Hi everyone, hope we're having a good holiday and hope you're also having a good chance to do a bit of revision as well. So we're actually going to be finishing up today on the notes for what you're expected to know based on what we did throughout term one. Now I was going to get these out at the end of week 10, but I ended up taking a bit of a holiday myself. But I'm putting that out now, so we should be able to have a chance to have a bit of a look at it, and hopefully this will help you with some of your revision. Okay, so now what we looked at previously was how we could work out, or what we had to know for our linear relationships, followed by our quadratic relationships and some of our inverse proportions, our reciprocal function there. So next, we're on to powers and polynomials. So what we have to be able to do is recognize features of the graphs of y equals x to the power of n, and this is a special thing that just basically means for all positive integers. So basically we need to know what y equals x to the power of n will look like for everything from so we need to know what it looks like for x squared or x to the power of 1, which is just a straight line, and x cubed, everything like that. So on this one, I'm just going to do as an example y equals x squared, and I'm also going to do y equals x to the power of 4, just as a way of example here. So when we've got x squared, it'll look something a little bit like this. It should be symmetrical. And one of the special features of y equals x squared is that we always end up being positive. So it says behavior as x tends to infinity and x tends to negative infinity. For y equals x squared, so as x tends to positive or negative infinity, y will tend to infinity for that one. So that's something that we need to be able to say. And the y equals x to the power of 4 will look pretty much exactly the same, but be steeper. Y equals x to the power of 6 will do the same thing. It'll look the same again. So x to the power of 6 will look the same again, but be even steeper. So all of our even powers will all end up looking the same. So what do the odd powers look like? Well, I'll just do a little diagram of these. Now our first odd power is actually y equals x, because it's sort of to the power of 1, but we tend not to write the 1. So it's y equals x, which we should all recognize as just a very straightforward straight line. But this also works for all our other odd powers, x to the power of 3. This one looks like so. And then we'll have y equals x to the power of 5, which will look pretty much similar but be steeper. So that's basically what we expect to see with all our various powers. And this one is as x tends to infinity, y will tend to infinity. But as x, now let's get that a bit further down so we can actually see it. As x tends to negative infinity, y will also tend to negative infinity. And that's the thing we need to be able to tell with those ones. Now that's for all positive integers, but if our number is, if our power is -1, we get the reciprocal function, which we can see down there. And if our power is 1/2, then we get the square root function, which we can see down here. And these ones, as x tends to positive or negative infinity, it should be pretty obvious that y tends to 0 either way. And this one, as x tends to infinity, y tends to also infinity. It may not necessarily look like it because it doesn't go up as quickly, but it does actually, because you can always get larger and larger values for x that you can throw in there. So you'll always also get larger and larger values for y there too. So that's what we've got there for our powers or for the first part there. Next up is to identify the coefficient and degrees of a polynomial. Now, a polynomial is something that looks like this one down here. Polynomial always looks like various x to the power of some positive integer all the way down to a constant, and then they'll all have coefficients of some kind like that. And the order of a polynomial is always the power of the highest non-zero term. So that's that one there. So the order for this one is 5, and the coefficients for each of these, we've got a coefficient of 1, coefficient of 3, coefficient of 2, coefficient of -1. Now we've actually got a secret hidden coefficient of 0 because there's no x term in here. So technically there's an x term that has a coefficient of 0, but we don't actually have it drawn in. And then we've got a coefficient of 5 for our constant term, or x to the power of 0, we could think of it as. So that's how we define the coefficients and degree of a polynomial. Then we need to be able to expand quadratic and cubic polynomials from factors. Now, when we're talking about a factor, we are talking about, just let me have a look back up there. I did blue. So when we're talking about a factor, we're talking about this. X plus 3 is a factor. X minus 5 is a factor. These are all factors. I'd like you to try expanding those. You should end up with the number that I've got down here. We've got 4x squared take 8x take 60. That should be, and this one should be x cubed take 5x squared take 2x plus 24. So you should be able to do or be able to reliably expand those ones without too much difficulty. And that's what we're doing here, expanding quadratic and cubic polynomials from factors, and we're turning them into this polynomial form. So that's our polynomial form, much like the one we've got up there. Okay, what's our next thing? So we need to be able to recognize key features of y equals x cubed, y equals a x take b cubed plus c, and this one here, including its shape, intercepts, and behavior. So let's have a look at our basic one first. So a basic one is y equals x cubed, and that looks a little bit like that. That's not going to be a perfect one. So that's y equals x cubed, but it'll look something like that. And what will happen with y equals, and I'll just get the exact form. Yeah, a x take b all cubed plus c. So this will be this same one here, but it'll be moved across by b and up by c. So it might have, this will be at the coordinates b, comma, c. And then it will look a little bit like this. It'll otherwise be the same shape. This is just like with our quadratic where it's been shift. This is the turning point form, or this is the horizontal point of inflection form for our cubic. So this has been shifted to the right by b and up by c. It's also been vertically dilated by a. So it's been stretched up if a is greater than 1, or squashed in if a is between 0 and 1. Or it may have even been flipped upside down if a is a negative number. So that's a possibility as well. So that's something you've got to bear in mind there when we're looking at that one. Okay, so next up, the next one was when we had, and I'll do this in green, y equals k, x take a, x take b, x take c, and this will just literally be and I'll put them all, well, it'll just be the one that passes through these 3 times like that, and this will be a and b and c. Those will be our 3 x-intercepts for that particular graph there. And then it'll be multiplied by some number there. Again, if that number is negative, it'll be flipped upside down. or it'll be stretched. And one of the ways you can work out is where the y-intercept happens to be, because that's just going to be k times negative a times negative b times negative c, or negative kabc when we multiply it all together. And that will end up being, and that will help us work out what k is if we happen to know the y-intercept. Okay, so that's just a little idea of those ones there. The behavior as x tends to infinity and x tends to negative infinity. Basically, if the x cubed term has a positive coefficient, y will tend to infinity with x, or negative infinity with negative, or negative infinity with that one there. But if k is negative, it will do the opposite. Or our x cubed term is negative, it will do the opposite there. So that's what we've got to think about. Next up, factorizing cubic polynomials in cases where a linear factor is easily obtained. So this is the tougher one, and I'm actually going to do it as a little example down below. And we're going to take this expanded form of x plus 2, x take 3, x take 4, because we know what it's equal to, we know what answers we should get. So we're going to just take that one and see what we can do. So one of the things we know, and I'm going to pretend we don't know these other two over here, but we know that x equals negative 2. So the whole thing equals 0 when x equals negative 2. That means that x plus 2 is a factor. So if x plus 2 is a factor, that means that we can rewrite this equation in the form x plus 2 in brackets ax squared plus bx plus c. And it's just up to us to work out how this equation down here matches up to the one above it. So the first thing we want to do is match the x cubed terms. Now there's only one way to get an x cubed term, that's to multiply x by ax squared. So basically we will know that x cubed equals ax cubed. So a is equal to 1. That was pretty easy, and most of them will have the answer of a is equal to 1, unless they're going to give you one really hard, but I don't think they will, because this is a fairly complex idea anyway. The next easiest one to do is to work out our constant term there. There's only one way to get a constant term. We do 2 times whatever c happens to be. So 2c equals 24, because this has got to expand into that one there. So c is equal to 12. Pretty straightforward. So that's our second one there. Now we can work out what b is using any of either this negative 5x squared or the negative 2x. I generally recommend using this term because it will be easier to work out than the other one. You're not going to be multiplying by as large a number. So how do we get an x squared term? Well, we can do x times bx. So we could do, that's going to be bx squared. The other way to get an x squared is, and the x squared term is to do 2 times ax squared. But we already know what a is, it's 1. So that's going to be bx squared plus 2x squared equals negative 5x squared. So we know that one. What's b going to be in this one? B has to be negative 7. That's the only way that it can end up being the right thing. So that's what we've worked out there. So we've worked out what a, b, and c are, and that means that our equation turns into x plus 2. A is 1, so we do x squared. B is 7, so we do take 7x. And c is 12, so it's plus 12. Now we need to factorize this. What two numbers add to negative 7 and multiply to 12? Well, they've both got to be negative numbers. So it's going to end up being, and let's get that over here. It's going to end up being x plus 2, and that's the numbers negative 3 and negative 4. So that's what we're able to factorize that into. So we're able to work out how to factorize. We know that x plus 2 is a factor. So we can factorize that and work out that this is our factorized form of that. Now, this is a bit of a tricky concept, but it's a good one to practice. So that one is, and it's in a whole bunch of different exam questions. So that's definitely a good one to have a bit of a practice on, because I can almost guarantee that it'll be in an exam. And next up is to be able to solve cubic equations using technology and algebraically, where a linear factor is easily obtained. So that's just working out when we look at this that when we look at this answer here, we know that x equals -2, 3, or 4. Those are, or if y equals 0, x equals -2, 3, or 4. That will be basically what our solutions end up being. Or you can be able to use your graphics calculator to do that. And the graphics calculator you might be able to see here, if you've had a look over here throughout this lesson so far, is that if I've got my x plus 2, x take 3, x take 4, there is a special function called expand, which does automatically do our expansions for us by doing action, transformation. We can expand, or I can even factorize that. Let's try factorizing that and see what it gets. Can give some funny results, so let's just see what it does. And yeah, that's factorized that successfully. So that's what we've got there. So next up, we've got graphs of relations. So there are a few different relations. Basically, these are our, I'll do that in blue. I think that looks a bit better. So these are our two different functions, or two different relations, not functions rather. So one of them is x squared plus y squared equals r squared, and that's going to end up being a circle with radius r. So whatever the circle is, the radius is r. Remember that the term on the right ends up being squared, so you've got to take the square root of that. And if it's x take a, y take b, both of these squared equals r squared, that'll end up being the center of this one will be at a comma b. Bear in mind that both of these are being subtracted. That's a bit unusual for when we're dealing with functions, but remember this is not a function, this is a relation. So we're subtracting both of these. It'll still have the radius of r in there, and that just moves it around. And we should be able to expand that and work with that. So yeah, that's not too bad. Then we've got y squared equals x. We should be able to recognize that this is our, I'll see if I can draw that so it's not terrible. There we go. So that is our parabola pushed on its side, basically. And it is also half of the square root function, y equals the square root of x, because in the square root function we don't draw, it's got to be a function, it's got to pass the vertical line test, so it can't have that bottom half on there as well. So that's what we've got for that one. It's got an axis of symmetry about the middle there. And so yeah, those are the graphs of relations. Next up, we've got functions. So we've got to understand that when we've got a function like f of x equals 3x squared, we are taking an x value, whatever it happens to be. So we're taking an input, and this is a common sort of drawing that people do. So we've got our input, and then we've got an output. And so the input might be, and this is a machine that will say square, then multiply by 3. So whatever number we happen to put in, 1, 2, or 3, we square it, then multiply it by 3. So that will put out 3, 12, and 27 as our outputs. Or if we just had x, it would put out the number 3x squared, just as an example there. So that's basically what a function is. It is a mapping between sets. So it's a way to map things from one side to the other. And it's a rule or formula that defines one variable quantity in terms of another. So one of the things about them as well is that you can only get one output for each input you put into it. So that's one of the reasons why you can do the vertical line test to make sure that it is a function, because it shouldn't have two outputs for any given input. So I'm going to be able to use function notation. That's just this f of x. Determine domain and range. Domain is the possible x values. Sometimes this will be an artificially constrained one, so they might say that, for example, x is between -2 and 5, so that will be our domain, or it might be a natural one. So for example, if we've got the function, let's just scroll down a little bit. So if we've got the square root of x, or f of x equals the square root of x, that has a natural domain where x has to be greater than or equal to 0, because you can't have a negative value in a square root when you're dealing with real numbers. Okay, so that's domain. The range is range is possible y values, but the range depends on our domain. So based on domain. So if our domain goes from -2 to 5, we only care about the y values between that x range of -2 to 5. We don't actually care about anything outside of that. So that's that. Concept of a graph of a function. Oh, sorry, this other one. Independent and dependent variables. Independent variables, you would have seen this in science as well. So independent ones are ones that do what they want, and the independent variable is x. It's independent, it does what it wants. The dependent one for this situation is typically y. Now y only does what x tells it to, so it is dependent on x. And x and y aren't always our variables. Oftentimes we'll have something like time and cost in dollars. So when you're working out what someone's paid as an hourly wage or something like that, well, it could be something entirely different, but one's independent and one is dependent on the first one. So yeah, that's that one. We should know the graph of a function. It's just your standard graph. You just got to be aware that when you've got your graph, that sometimes this is y at the top here, or sometimes we actually instead write, or sometimes we write f of x instead of writing y for our vertical axis when we're talking with functions. But oftentimes we'll just deal with it as y, or it'll say that y equals f of x somewhere in the question. Now we've got our translations, and I've just put this in here because this is basically what we need to know. Now we did this in a previous lesson, but basically when we add outside our brackets, we're going to move up or down. So that's the f of x plus a, or x cubed plus a as an example. That's just moving up and down. Or f of x take b, that moves down. If we do it inside the brackets, we do a horizontal translation, or a left and right. When we add inside the brackets, we move left. When we subtract inside the brackets, we move right. When we multiply outside the brackets, we do a vertical dilation. So that can be, if it's a number greater than 1, then it gets bigger. If it's a number less than 1, it gets smaller or flatter. Then when we're inside the brackets, it's a bit contradictory, but inside the brackets, it gets more squashed in when we multiply it, and inside the brackets, it gets more stretched out when we divide it. So that's the one that's a little bit opposite of what you may think. And also we've got If it's a negative outside the brackets or outside that f of x, then it's flipped vertically. And then if it's a negative inside that, it's flipped horizontally. So that's a little summary of how we expect those to work. The last thing it says is that you can recognize the distinction between functions and relations and apply the vertical line test. I've covered that a few times during this. Hopefully that's not too tough for you anyway. So that's all good. Basically, if you can draw a vertical line and only ever cross your line a maximum of once, it is a function. Otherwise, it is not a function. So yeah, that's that. Anyway, I hope that was useful for you, and hope you've been having a good holiday, as I've said. Just so you know, throughout this entire procedure, I've had this guy on my lap, and he's been nice and quiet. So, but he's a good little boy, and he will be helping me out over the rest of the year as we do more of these videos. Now he's starting to stir because I've woken him up. Anyway, have a good day, and I will see you when we get back. Bye.